Hi everyone, welcome back to another GCSE Physics session. Today's session is going to be starting the topic of space physics. So we're going to start with the solar system and a little bit about all the things inside of it. At the beginning, we will, however, just do a little bit of a recap of magnetism and electromagnetism. As always, this session is recorded. It's 1 hour long and it will be up on YouTube as soon as possible. If you don't know me already, I'm Preshayla. I'm the GCSE Physics tutor for the online school. I study physics at Loughborough University and it's my 4th year as a tutor. So what we're going to cover today in a bit more depth is a recap of electromagnetism, understanding the structure of our solar system and what it consists of, describing the process of the formation of our sun, describing the life cycle of a star, and understand how fusion processes produce elements in our Earth. And then we'll go over some example questions and we'll have time for questions at the end. Okay, so a quick recap on everything to do with magnetism and electromagnetism. So we started off with magnetic fields and the fact that if we have a permanent magnet, it produces its own magnetic field around itself. So that's a permanent magnet. But an induced magnet is a material that becomes a magnet when it's placed in a magnetic field. Okay, so two different types of magnets that we looked at: permanent and induced. So a magnetic field is this region around a magnet where a force acts on another magnet or on a magnetic material, such as iron, steel, cobalt, and nickel. So they're the main magnetic materials that we have. And we also looked at the kind of rules about magnetic field lines. So you'll see that there are some magnetic field lines here, which are these black lines with arrowheads on. Now, we talked about the rules, and some of those rules were they don't ever cross. They always point from north to south. So you can see that the arrowheads always go from north to south, and what they look like. So for a bar magnet, for two poles attracting, for two poles repelling, and so on and so forth. Then we went on to look at how current and magnetic fields are linked together. So if we have a current carrying wire or a conductor, a magnetic field will be created around that wire. So we have the wire pointing in some direction and the magnetic field is circular around it. So it's one circle, big circle, expanding outwards, as we can see in the diagram. Okay, so a current carrying wire produces its own magnetic field around itself. So magnets do that, but so do current carrying wires. Now, the strength of that magnetic field that is created by a current carrying wire depends on A, the current in the wire, and B, the distance from the wire. Okay, so two factors that we need to know and how they affect the magnetic field produced by current. We also looked at the right-hand grip rule. So we have two rules in this topic which can sometimes get a little bit confusing. The first one is right-hand grip rule. So you're going to take your right hand, do a thumbs up, point your thumb in the direction of the current. So if the current's going upwards, you point your thumb upwards, downwards, you point your thumb downwards. And then whatever way your fingers curl round is the direction of the magnetic field. That can be done up, down, left, or right. Okay, so if you are asked in an exam to draw the magnetic field, make sure you use the right-hand grip rule first to find out the direction of the curl of the magnetic field. Okay. Then we went on to look at what a solenoid is. So outside the solenoid, which is a small coil of wire, the small magnetic fields from each wire cancel each other out and the outside field is much weaker. So inside the solenoid then, the magnetic fields of each little coil add up together and cause a much stronger magnetic field inside. So inside they add up, outside they cancel out. So inside much stronger than outside. And a solenoid creates this magnetic field because it takes so many little different magnetic fields and adds them up. Okay, so solenoids are used in electromagnets. So we'll look at that in a second, but it's a nail or an iron core with a coil wrapped around it, which is a solenoid, and it's used to make an electromagnet. Then we looked at this equation, F equals BIL, which basically talks about the motor effect. So we know that with the motor effect, if we have a current carrying wire and we place it in a magnetic field, we're going to get some sort of motion. And this is governed by the equation, force equals magnetic flux density times current times length. B is magnetic flux density and is measured in Teslas. Then we went on to look at an electromagnet. So this is when we wrap a solenoid, a coil of wire, around an iron core. Could be an iron nail, could just be an iron core. And it becomes an electromagnet. Now that electromagnet can be turned on and turned off. Can be demagnetized and magnetized. But it needs some sort of battery, some sort of power to make it magnetized. Okay, so the iron core is there to increase the solenoid's magnetic field strength. Then we looked at some applications of electromagnets. So we looked at the scrapyard crane. So scrap vehicles are lifted in a scrapyard using these electromagnets, and the vehicle sticks to the electromagnet when the current is passing through the coil, so when it's switched on. And when that current is switched off, the vehicle falls off the magnet because the electromagnet has been demagnetized. So it's all about this magnetization and demagnetization of electromagnets. We looked at a circuit breaker, which is sort of the same thing. And when the current gets too large, the electromagnet is able to open the switch. So it attracts the switch open and breaks the circuit. Then we looked at the electric bell. I won't go into too much detail about that, but it is another application, and this demagnetization and magnetization of the electromagnet makes that ringing sound by breaking and completing the circuit. The relay, again, another one, and this is used to switch machines on and off. So by putting a small current in the electromagnet, we can turn on a machine that has a large current, therefore saving power. Then looked at the motor effect. So remember, this is a current carrying wire in an existing magnetic field. And what that means is because the wire creates its own circular magnetic field around itself, when you place it in an existing magnetic field, you have two magnetic fields that kind of collide with each other and exert a force on each other, which makes the wire move. Remember, it's all governed by Fleming's left-hand rule. So we have the thumb motion, the first finger field, and the second finger current. And you can point your two fingers in whichever kind of quantities you have, and the way that your other finger points is the way that it moves, the field, or the current. Okay, so make sure you always use your left hand for that. The electric motor is this application of a wire moving in a magnetic field, and the speaker takes these electrical signals, puts them through an electromagnet which can repel and attract a permanent magnet, and then the speaker cone is attached to that, so it feels those vibrations and changes them into air vibrations. Then looked at the generator effect. So the generator effect is by moving a wire in a magnetic field, we can create a voltage and therefore a current. So it's all about electromagnetic induction, all about creating a voltage by moving a wire in a magnetic field. However, if that wire is stationary in the magnetic field, we do not get a potential difference. It must be moving constantly. Now, how can we increase that potential difference? Well, we can increase the speed of the movement, the magnetic field, or the number of turns in the coil. How can we change the direction of the voltage? So get it kind of an alternating current is by moving the magnet out in an opposite direction or moving the other pole into the magnet, not both at the same time. An induced current generates a magnetic field that opposes the original change, either the movement of the conductor or the change in the magnetic field. So what this means is if we push the south pole in, the current's going to go the opposite direction. Then we looked at the AC generator, which takes this wire in a magnetic field and only allows it to do a full turn. So an AC generator only allows the coil to do a full turn. Okay, it allows it to do a full turn, and what that means is the current constantly changes direction. So because the coil constantly changes direction because it's allowed to do a full turn, the current will also constantly change direction. And this is how we get an alternating current. So you can see that it constantly changes direction. It goes from positive to negative, back to zero, and so on. Okay, and then we went on to look at the DC generator. So DC generator is very, very similar, but instead of a full turn, it now only is allowed to do a half turn. Okay, so the wire goes halfway, gets stopped, reverses, halfway, stops, reverses. Okay, that's all done with a split ring commutator, and because we're not changing the direction of the current, we get a DC current, a direct current that only ever flows in the same direction. So you can see that it's always positive. Then we looked at how speakers use sound waves in a little bit more depth. Then we went on to look at transformers. So transformers are these devices that can increase or decrease the voltage of an alternating current. So they take some input, they use this ion core to transfer the magnetic fields, and then they get an output. We have two types of transformers, step up and step down. Step up means it increases the potential difference, and step down means it decreases the potential difference. It's made from two coils either side of a ion core. So how does a transformer work? Well, it takes a primary input voltage and creates an alternating current. We then have, because we have an alternating current, we have a changing magnetic field. That changing magnetic field gets transferred by the ion and is strengthened by the ion. We then have a changing magnetic field come out on the other side, which creates a secondary output voltage. That secondary output voltage is then changed into an alternating secondary current. So this voltage drives this current, this voltage drives this current. Looked at the transformer's equation, which is primary voltage input over secondary voltage output, is the same ratio of the number of turns on the primary coil divided by the number of turns on the secondary coil. So we can work out one of these four values by knowing the other three and remembering to practice our rearrangement of that equation. Looked at how the national grid uses transformers by stepping them up after they're created, generated. After the electricity is generated, they step it up to be transferred along the cables. And so we have a really high potential difference in the cables, which means we have a reduced current, reduced heat, reduced power loss, and increased efficiency. It then steps it down before it goes to our houses. Okay, so efficiency, sorry that it's kind of gone over each other, but efficiency of a transformer is nearly 100% efficient, and we assume that it is. So what we can say from that is that the power that goes into the transformer is the same as the power that comes out of the transformer. So power coming in is PP, so primary power, equals secondary power. Now we know that our equation for power is P equals IV. So we can split primary power into primary voltage times primary current, and split secondary power into secondary voltage times secondary current. So we have another equation, which again can be quite complicated to rearrange, so practicing our rearrangement on this equation as well. You don't need to remember them, but you do need to know how to work with them. Okay, so moving on to the content for today then, we're going to be looking at the solar system, quite an exciting part of physics, and not so much maths involved at all. Okay, so here you can see the 8 planets in our solar system in kind of decreasing order from the sun. So we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So you can see that we've got 8 planets, M, V, E, M, J, S, U, N. Okay, now you need to remember what order they come in distance from the sun. So some people like to come up with mnemonics. The one that I personally use is, my very eager mother just served us noodles. So if you want to remember that, I'll write it down. However, obviously you can come up with your own. So if you do have any of your own, do share them around. Someone else might like yours better than mine. Cool. Okay, so our solar system has one star, and that's the sun. Okay, so our sun is our star. It's what gives us light, and it's what gives all the planets light. Yeah, so 8 planets, 1 sun, 1 star. Now, we have a moon on Earth, which I'm sure you all know. We have 1 moon, and that's it. Now, that's called a natural satellite. A satellite is something that orbits a planet. So a natural satellite is a moon, okay? Earth's moon is not the only moon out there. There are lots and lots of moons for all the different planets. All the different planets have their own moons, okay? And that's a natural satellite. We also have man-made satellites, which we'll look at after, but our moon is a natural satellite. Some planets have lots and lots of moons. Mars has 2 moons, Saturn has a few moons, Jupiter has a few moons, and Mercury and Venus have 0. Okay, so it really varies between the planets, but it's important to remember that our Earth is not the only planet that has a moon. Okay, now our solar system, and the reason that it's called a solar system is because, I'm sure you know, solar relates to the sun. So that's kind of how the solar system is named. It's the sun system, all the planets and our sun. But our solar system is such a tiny part of the whole galaxy that we belong to. Okay, so our solar system is a tiny, tiny little part in a huge Milky Way galaxy. That's the name of our galaxy, Milky Way. There's loads of galaxies out there in space, loads and loads and loads. So we are a very, very tiny part in space. I mean, you can't even begin to imagine how tiny we are. One comparison that I can do for you to kind of make it make sense in your head is that if the Earth was a grain of sand, the sun would be the size of a tennis ball. So if our sun is that much bigger than us and our solar system is only a tiny part, you can see just how very small we are. So what kind of other things can we find in our solar system? We know that we have 8 planets, we have a sun, and we have a few moons, but what else is there? So there's these things called comets. So comets are frozen bits of rock that move in elliptical orbits. So we need to know that they're frozen and that they move in elliptical orbits as the key points for a comet. So frozen and elliptical. Now, meteors are small bits of rock that burn when they enter the Earth's atmosphere. So meteors are slightly different and are not frozen. Then we have dwarf planets and asteroids. So dwarf planets, I'm sure you know Pluto got made a dwarf planet, quite sad. And then we have even smaller planets, which are asteroids. So asteroids are basically like failed planets. So too small to become a planet. They're not big enough to be a dwarf planet, but they're too big to be a meteor. So they sit in that kind of in-between phase where they just didn't quite make a planet. Okay, so that's other things that we have in our solar system. Pluto is still a part of our solar system. It's just not considered one of the planets anymore. Elliptical is this shape here. Sorry, I didn't mention that. Elliptical is kind of like an ovular shape, not quite a circle, a squish circle, but it's still regular. Okay, it still follows that nice oval pattern, but it's not completely circular. Okay, so we need to talk about the formation of our sun. How did our sun come to be? So the sun was formed from a cloud of dust and gas called a nebula. All stars start from this. Okay, all stars, no exceptions. All stars form from a cloud of dust and gas, also known as a nebula. That nebula is pulled together by gravitational attraction in space. Okay, so objects of mass have gravitational attraction, so they are attracted together and they come closer and closer and closer together. So the sun is formed at the center of this spinning cloud of dust and rock and gas due to gravitational attraction. Now the sun has obviously a lot of heat, and it starts to evaporate that ice. Okay, so the ice in the nebula, and drive gas away from the solar system but leave the rocks behind. So because it heats up, it evaporates the ice and leaves rocks behind. Now, this is what caused the solar system to come into effect. So the rocky planets are formed near the sun, so Mercury, Venus, Earth, and the gas giants are formed further away. So the gas giants are Jupiter and Saturn. Okay, so this is how the solar system came to be and why they are in the order that they are. Gas giants, Jupiter and Saturn, and the rocky planets, Mercury, Venus, Earth. Okay, so how the sun came to be and how the solar system came to be. Let's go a bit more in depth of the star life cycle of a star the size of the sun. So how does it all work? What actually happens? What is the process that's going on? So the particles in the clouds pull together under their own gravitational attraction, and that means that the particles speed up. So there's a force, a gravitational force, acting on it and squishing it and making it more pressurized, and it has to speed up. Okay, so it starts speeding up, the clouds merge, they get denser and denser, and they start to squish down. That becomes a protostar. So it goes from our nebula to a protostar. So a protostar is the beginning of a star. Now the particles keep getting denser, they keep colliding more, and it keeps getting hotter. They get denser, they collide more, they get faster, they get hotter. So it's really this high pressure situation that's constantly evolving. Now, this gravitational potential energy gets transferred into thermal energy. So we know that we have gravitational energy pushing down on our protostar constantly. And at some point, that gravitational potential energy gets transferred into thermal energy. So the star begins to heat up more and more. And if it gets hot enough, then the hydrogen atoms that we have fuse together and it gets hotter and brighter and starts to shine. Okay, so that's how a star works. A diagram here for you just to kind of make it a little bit more clear. So if you follow the left-hand path of the diagram, this is the general life cycle for a star about the same size as the sun. If you follow the right-hand side, it's the life cycle for stars much bigger than the sun. So you can see that no matter what, it always starts off as a nebula and it always goes to a protostar. Then it becomes what we call a main sequence star. And if it's the same size as the sun, it's a red giant, a white dwarf, then a black dwarf. If it's a bit bigger than the sun, it's a red supergiant, a supernova. And then after it's a supernova, it kind of collapses in on itself and either becomes a neutron star or a black hole. Okay, so right now our sun is a yellow dwarf and it will become a red giant. So what's a main sequence star? A main sequence star is a star which is in the main stage of its life. Okay, it's in its kind of prime, it's in its main stage of its life. The energy in the core keeps it hot, so fusion continues and it can continue to shine. The core gives out radiation in all directions. So it gives out this heat radiation in all directions. Okay, so that's a force coming from the inside and pushing outwards. So we have a force pushing outwards, but we also have a force pushing inwards, which is the gravitational force. So we have radiation coming inside out, and we have gravitational coming outside in. Okay, so because we have this kind of balance of the two forces, outside force and outside inside force, the forces stay in equilibrium. Okay, so because the forces stay in equilibrium, it allows the star to be stable. So forces being in equilibrium means that the star will be stable. And it stays in equilibrium for a while whilst it's in the main sequence until most of the hydrogen has been fused to create helium. So that's what's going on in the sun. Hydrogen keeps fusing to create helium. Okay, so how did all of the elements in the Earth come around? So how did iron get here? How did aluminium get here? How did oxygen? How did all of those different elements that we have, silver, gold, how did they all get here? That is because of stars. Okay, so you might have heard that kind of famous popular saying that we are all kind of 99% stars. And yes, that is partially true. We are pretty much made up of the remnants of dead stars. Okay, so fusion processes in stars produce these elements. So they're the byproducts of these fusion processes. So we have in a lot of stars hydrogen fusing to create helium, and that creates kind of byproducts in the process of doing so and creates all of our naturally occurring elements. However, elements heavier than iron are produced in supernova, so much, much bigger stars, because more energy is needed to create those elements. So if the elements are lighter than iron, then they can be created in our normal kind of stars. But if they are heavier than iron, then they must be produced in a supernova because much more energy is needed to produce them. Now, the explosion of this supernova distributes the elements throughout the universe. Okay, so Earth gets some, our solar system gets some, some other galaxies will get some. And so this explosion of the supernova distributes these elements, which creates life, which creates planets, which creates everything. Okay, so that is all of our content for today. I do have a quiz for you guys, seeing as you quite enjoyed it yesterday. So actually, before we do so, I will just answer a few questions that you guys have put in the chat. Okay, so what is a solenoid for? So going all the way back to electromagnetism, a solenoid is used to wrap around an iron core and create an electromagnet. So we use a coil of wire instead of a straight wire because each of the little magnetic fields of each coil can add up together and create a stronger magnet. What does magnetic flux density represent? This is a really good question. Magnetic flux density is kind of the strength of the magnetic field that we have. So if I go back to here, so you can see that there are lots and lots of lines in this section here, right? There's 1, 2, 3, 4, 5, 6, 7, 8, 11 lines in this circle. Okay, 11 lines in this circle. That is where the magnetic field is really strong. But when we go outside, the lines are less close together and the field is weaker. Okay, so you can say that the magnetic flux density here is much higher than the magnetic flux density outer. The sun, okay, so a normal star will die. Will the sun ever die? Not in the lifetime of humans. So 500 million years the sun has been burning for, and scientists say that it will continue to burn for 500 million years. Did the sun have to go through the same system as the other stars? Yes, absolutely. Our sun went through the exact same process. Is it possible to destroy a black hole? Don't know. They haven't kind of proven anything to do with black holes. It's a really slow progressing area of science, so I couldn't say. Why don't we count Pluto? Pluto is just too small to be considered a proper planet. It's not quite in the kind of specifications that astrophysicists have put out for a planet to be a planet. It just doesn't quite reach that size. Okay, so I think that's all the questions in the chat. Sometimes neutron stars can collapse into black holes. Yes, they absolutely can. Neutron stars and black holes are these very, very dense objects. Okay, so I think that's all the questions there. What is a black hole? Someone said. So a black hole is this kind of void in space, and it kind of sucks everything into it. Once something's in, it cannot escape. Okay, because the kind of force of the black hole is so strong on the objects that are in it, nothing can escape it. So it's a very, very dense object. Black holes are not needed for your specification, but if you guys are interested, then it's definitely a really interesting area of space to look at. Okay, I think we'll move on if there's no more questions, and we'll go on to our quiz. Okay, so same kind of thing as yesterday. You need to put in the game code at joinmyquiz.com. So here it is. I'll put the link on the chat as well. So just go to this website, joinmyquiz.com, and enter the game code 679336. If you can't do that, I've put the link on the chat for you guys. Okay, we've got 19 of you on so far. Let's see if we can get a few more of you guys on. Okay, I'll give us 2 more minutes for people to get on to the game. Okay, hopefully you've had a chance to get onto the game. If you haven't, then the link is in the chat and you can still join. Cool, so let's start. So they are all multiple choice, and you do have 30 seconds for each answer. So do just take your time. You don't need to rush. I'd rather see accuracy than speed. Cool, we've got 87% accuracy. That's really good. Let's try and keep it at that level. We'll dropping our accuracy slightly. Let's try and get it back up to 80 if we can. Remember, you don't need to rush. You have 30 seconds for each answer. About halfway through now, it looks like. Okay, so you're getting really, really close to the end. Well done to PC, who's currently in the lead. Okay, I'll give us 1 more minute. Oh, back up to 75% accuracy. That's really great. Okay, so let's start going through the answers then. So first of all, what is nebula? Loads of you got this correct, which is really great. A nebula is a cloud of dust and gas. So it's what all of our stars start off with. What causes dust and gas to pull together and form a protostar? So dust and gas pull together to create a protostar using gravitational attraction. What two things balance and keep a main sequence star in equilibrium? So that's gravity coming from the outside in and pressure from radiation coming from the inside out. Okay, so radiation, heat radiation, comes from the core and is pushed outwards. Gravitational attraction acts on it and is pushed inwards. What is nuclear fusion? A nuclear fusion is small atomic nuclei such as hydrogen combining to form larger nuclei such as helium and releasing energy in the process. Where do elements heavier than iron form? They form in supernovae, and the reason for this is because Elements heavier than iron need much more energy to form, and that energy can only be found in a supernova, not in a normal star. What will the sun become in the next stage of its life? I did mention this briefly, but the sun will become a red giant. Which of a possible two stars form after a supernova? After a supernova, it will either become a neutron star or a black hole. Which of these is a dwarf planet? Mostly all of you got this correct. It's Pluto. Which of these is a natural satellite? So a natural satellite, remember, is the moon. The other two are man-made satellites. So they were made by NASA and put up into space. What shape are the orbits of comets? They're that elliptical shape. So if you remember, it's that kind of squashed circle shape like this. And they are regular. So irregular would not be the correct answer in any case. And then which of the following is not a part of our solar system? The moon is, the sun is, the Milky Way isn't. The Milky Way is our galaxy. So the solar system belongs to the Milky Way galaxy. Okay. Which body was the first stage in the formation of the sun? That's a nebula. Remember, all stars start off as a nebula. What sort of reaction mainly happens in the sun? That's nuclear fusion. So the sun is constantly fusing hydrogen to create helium. Lots of you got that correct, which is really good because that is a little bit more complicated. And lastly, what is a comet? This one is a little bit more confusing because all the answers are quite similar. So yes, they are rocky material, dust and ice, but they orbit the sun and not the Earth. Okay, so that's all the answers. I hope you guys enjoyed the quiz. Well done to PC, N and SB who were top 3, and there was not much in it, so well done guys. Okay, so let's move on to some example questions. Now, one thing to note about space physics, and especially this first half of the topic that we're doing, is a lot of the GCSE exam questions are fill in the gaps. Okay, they're not very inventive with their questions. They tend to do like fill in the gap questions a lot of the time, or the other end of the spectrum, which is process questions. So describe the formation of a star. Really, really common question, a good 6 marker or a 4 marker. But yeah, as I said, they're kind of quite nice with these kind of fill gap exercises, which kind of takes some of the pressure off for you, because also they can't test mathematics, so we don't have any formulas in this half of the topic. So it is important that you know your process as well, and you know your qualitative really well for space physics. Okay, so let's have a go at this first question. So if a red something star is large enough, it may eventually blow up in an explosion called leaving behind a very dense star. So what could fill in those gaps? If a red something star is large enough, so put your answers in the chat or in the Q&A. What would be the fill in the gap using those words that you've been given in the box? Ten more seconds to get your answers in. Okay, if a red giant star is large enough, it may eventually blow up in an explosion called a supernova. Okay, so that explosion is called a supernova. And after it does this supernova explosion, it then can go into one of two stars, either a neutron star or a black hole. So the word that we would be looking for here is a neutron star. Remember, they're very dense, so very dense neutron star. Okay, you've been given this passage from a science magazine. So a star forms when enough dust and gas are pulled together. Masses smaller than a star may also be formed when dust and gas are pulled together. What is the force that pulls the dust and gas together? So what is that force that creates this kind of compaction of dust and gas? So that would be gravitational, or gravity is fine as well, not weight. Personally, I would prefer gravitational. Okay, and then complete the sentences. The smaller masses may be attracted by the star and become what? So they may become planets, yeah? Our nearest star, the sun, is stable because the gravitational forces and the radiation pressure are what? So if you remember earlier, I talked about the forces going outwards and the forces going inwards, and there's some kind of condition that they need to be for the star to be stable. So what is that condition? What are the forces? They are in equilibrium. Okay, so they're in equilibrium, or they are balanced, imbalanced, they're equal, any of those are fine. Okay, so if those gravitational forces and the pressure from the radiation coming from the inside are balanced, then we have a stable star. Now the sun is one of billions of stars in the galaxy called the what? What is our galaxy called? This one should be quite easy for you guys. It's the Milky Way. Yeah, so our sun is in our solar system, but our solar system is in our galaxy, which is the Milky Way. Then there's loads and loads of galaxies in the universe. Okay, this one's, again, not too hard. Starting with the smallest, list the following in order of increasing size. So our smallest is going to be our Earth, then our sun, then our galaxy, the Milky Way, then our universe. So again, we have this importance of when a sun or a star is stable, the forces inwards and the forces outwards balance, okay? So they are equal to each other. Very important aspect of a star being stable. So you can see that the same questions come up time and time again, which is why I've left them in, so that you can see just how often and how uninventive they are with their questions. So again, we've got a fill gap exercise, and we've got what is the name of our galaxy? The sun is one of many what of stars in our galaxy. So let's first of all do our fill gap. So stars form when enough dust and what from space are pulled together by what? So dust and gases form and are pulled together by gravity to form our protostars. Stars are able to give out energy for millions of years by the process of what? So what is this process that allows a star to keep going? Why is our sun still going? What does it do constantly to allow it to keep going? it does fusion. Okay, so it's constantly fusing hydrogen to create helium, which is why it can keep going. So the correct answer there would be fusion. The sun is one of many. Okay, so this one is less obvious because you've got millions and billions, and although it might seem trivial when we're talking about space, it actually does make a big difference. So the sun is one of many billions of stars in our galaxy. Millions is actually not that much. Billions is more on the scale that we want to be talking. Remember, billions is 1,000 times a million. Yeah, so it's easy to get kind of caught up in, oh, they're all just big. But actually, there's a big difference between millions and billions. So it's about differentiating between the two. And actually, there are billions of stars, not millions. Millions is way too small. Name of our galaxy, Milky Way. That's fine, we know that. Okay, so let's move on to the life cycle of a star questions. So this diagram shows part of the life cycle of a very large star. So giving you a hint, it's a very large star. Okay, so it's going to follow the right-hand path of that diagram that I showed you. So you've got 4 words here, again, a fill gap exercise. The star is stable. The star expands, forming a what? The star collapses. The outer layers explode as a what? The center collapses further and further until it finally forms a what? Okay, so if the star is stable, we know that it can start to expand. Okay, now we know that it's a very large star, so it's much, much bigger than the sun. So it's going to follow that right-hand path of our flow diagram. Now, you may not remember, but the first kind of thing that it gets to is a red supergiant. Okay, so if it's bigger than the sun, it's going to become a red supergiant. Then the star collapses and the outer layers explode. That is exactly what is called a supernova. Okay, so the star starts to collapse in on itself and explode. So that's a supernova. The center collapses further and further until it finally forms a what? Well, we know that a supernova can go to one of 2 things, which is a black hole or a neutron star. So this would be a black hole. Okay, I think we'll stop there because we've got 2 minutes left of the webinar. I hope you guys enjoyed today's session. I hope you enjoyed the quiz. And we'll be carrying on space in next week, the beginning of next week.
Brilliant, thank you Preshayla for today's session. Thanks so much guys for taking part in the quiz. That was really great. If you join us for any other sessions, then we've got English literature coming up and then maths and chemistry this afternoon. But if not, then see you in a physics session next week. Just a reminder, we don't have any tutorials tomorrow as it is the bank holiday. So have a lovely bank holiday weekend and see you all in another session soon. Bye.
Bye, thank you.